Today I will be showing you very short snapshots from my diary from this winding trail of multifaceted materials futures. And this journey actually began already 20 years ago from a place not far from here in Nanotalo, when my first research internship advisor came to the coffee lobby to pick me up, and she asked, "Oh, are you the one who wanted to work with renewable materials and sustainability?" And yep, that was me. And sustainability has, of course, been the key driver of my work ever since. And back then, as well as today, I feel that I'm standing in this crossroads of very loud noises, a very congested traffic jam. And on the other side, we have these voices of more and more pressurizing eco-catastrophe. On the other side, we have the potential of more and more advanced functional materials. And of course, the key question is then, how can we implement these materials for the greater good of our society and for the planet? So after this research internship, I then went ahead and did a PhD, did a postdoc, and started my research group 6 years ago here in Aalto. What was clear to me 6.5 years ago was that sustainability is a moving target. It's not that easy to define where we are heading for. So if you're a leader of a research group, you are still expected to give a target. So one target that we started with was defossilization, which pretty much just means to prepare materials that are completely independent of fossil fuel sources. We then started to work with this statement that anything made of glass or fossil fuel-derived polymers could be replaced by biosourced materials. And within these years, we have shown that we can do different type of tunable optical films. We can do almost anything electronic from purely biosourced materials. So back in 2024, we demonstrated a pressure sensor that you can also see here that is completely made of biosourced materials and is completely biodegradable. So you could, for instance, imagine it inside your gastrointestinal tract. Then we have also done materials for lightweight acoustics and responsive textiles completely from biosourced materials. And these are the two examples that I will focus next. Yeah, so I mean, if we are going to reach carbon neutral Finland by 2035, or EU's target of climate neutrality by 2050, we are really in a hurry to bring up more materials that are carbon neutral or carbon negative. And if we now start from the acoustics and insulation part, if we just think about Europe, and if we just think of the capacity of the existing materials without even implementing anything new, 50% of the heating energy could be saved in buildings if we just implemented better insulation. Of course, this concerns more about heat insulation, but heat and sound sort of go hand in hand, and often the same material serves both for heat and sound insulation. So here you can see a typical material used in our walls for sound and heat insulation. It's rock wool, and this is a scanning electron microscopy picture of it. One first step that we took on this field was that we showed that something that performs similarly or even better can be actually just prepared from pectins that you can derive from either apple peel waste or citrus waste. One additional benefit that these materials have as compared to rock wool or glass wool is that they are much more lightweight and could then also serve in moving vehicles or elevators or somewhere where the lightweight is an advantage. So we are going to cut some corners straight, and here you can see the materials that we prepared from pectin. By changing the concentration of salt in the solution, we could actually modify the morphology quite some. And now if you look at the performance in the sound absorption measurements, you can see here the yellow line is just a regular glass wool. And as you can see that by changing the material composition of pectins, we can actually reach materials that outperform glass wool at all the measured frequency ranges. So yeah, this is of course promising as a first model material to this direction. And now we are moving for using more like industrial waste for the same purpose. So we have, for instance, demonstrated that faba bean hulls from food industry can be used for the same purpose. All right, switching gears from acoustics to textiles. Textiles is also a field where we really, really need defossilization. So if you think about textile fibers that are produced today, approximately half of them are fossil fuel derived. Most of it is polyester, but then there is also a big portion of polyamides. The energy use and the CO2 emissions are highest at the initial stages where you synthesize or spin the polymer. So this is then an interesting task for all of us to try to intervene there. And why we started originally to work with polyamides was that this is actually a staple material for different type of smart and e-textiles, which is also a field that we are exploring. Yeah, so again, a lot of work presented in very few slides. But what we wanted to do first was that we wanted to synthesize polyamides completely from bio-based monomers, starting from castor oil. And importantly, we wanted to drop the melting temperature of the polyamide so that we can spin at a lower temperature and less energy is consumed. This then also brings an additional advantage that if you're able to process at lower temperatures, we can also incorporate biomass in the process so that it doesn't burn while doing it. So what we did was that we synthesized copolyamides. We then compatibilized starch with a new method so that we could actually have 50% of our polyamide just starch. And this was not all of it. So then we also went ahead and made this type of textile actuators out of these. And here you can see our fabric prototypes where we can convert just the ambient heat energy into the macroscopic motion of the whole textile. And here the beauty is, of course, also how you integrate these small actuators into real macroscopic species so that the small motion gets amplified into bigger one. Of course, I mean, it's a fair question where you might want to use these. This is also, I would still call fundamental research. But you can imagine them as, like, let's say, weather adaptive interior textiles, or also on their part helping in climate adaptive buildings. Yeah, another nice thing you can do with polyamides is that you can, of course, functionalize them with something that converts light into heat and then converts this heat into motion. And here is our first example of how we could implement photothermal particles into same copolyamides. And with this, we can also then use laser light, which allows us to target very small part of the actuator, and that can then bend it to whatever direction you are shining the light from. So here you can see that simple light beam can be actually converted into quite large macroscopic motion. And also where this work is going now is that we are moving towards actuators that can be actuated with pure sunlight and potentially then go towards sun tracking applications. So you could, for instance, imagine solar cells that can just always bend towards the sun. All right, then this is about defossilization, but is it really enough for sustainability? And I want to argue that just defossilize is, of course, not enough, since we know that from life cycle assessment, also the use phase of the materials brings a lot of environmental impact. And one potential solution for extending the use life is to move towards multifunctionality, so that the same material could then serve multiple purposes and potentially by that extend their usage life. So here I want to take an example from the field of solar cells. And this is also a long process of many different works. But what we did is that we started from simple leek leaves, and from the observation that when you are in the kitchen and do food, you can see that when you wash leek, the droplets actually fall into preferential direction. So leek has this type of anisotropic wetting by behavior. If you're interested, I'm really happy to talk more about the details, but now just for the interest of the time, we developed a method where we can translate the surface structure of the leek leaves onto different materials, for instance, on cellulose acetate or PDMS. It has very interesting optical properties, slide quite nicely, and it also retains the same property than those leek leaves. So if you just drop water droplets, they will start to fall on one direction. And if you then have some dirt on the leek surface, you can just drop water droplets and the dirt will collect into one spot. So it is so-called self-cleaning surface. Then what we can do is that we can develop new kind of encapsulation methods where we take perovskite solar cells, we dip them into PDMS, and upon the dipping process, we apply this translation of a pattern. So now we have solar cells that have the leak surface pattern on top of them. Here you can see the solar cells in their natural environment here in Otaniemi. So we could show that this encapsulation is multifunctional. It protects the solar cells from the environmental factors, so allows them to be in use for a longer time. And also, thanks to the interesting optical surface structure that is derived from the leak leaves, the power conversion efficiency of these solar cells increased 8% as compared to non-patterned surfaces. So this tells us that by combining different type of bio-inspiration strategies and new materials, we can reach something that can be truly multifunctional. But then again, is it still enough for sustainability to defossilize and to multifunctionalize? And I mean, of course, once again, I need to argue that we are still on the road. It is not enough because we also need to bring into the equation the planetary limits and preserving the life here also for others than just humans. So how can we then move forward? So this is something as a leader of an interdisciplinary team aiming for holistic sustainability. So I've been thinking that we need to implement more rigorous reflective practice. And one goal here is also that through this reflective practice, our relationship to materials need to change. As a part of this reflective practice, here are some questions that we work with, and I also want to work with in future. And this is also an invitation to join the reflective practice for finding better questions. But I think we need to ask how much refining is necessary when we prepare materials for whatever uses. How can scenario building help finding optimal usages for different type of site and waste streams so that we have the right waste or the right site stream going for the right application? Also, what type of multidimensional understanding and interdisciplinary understanding do we need for holistic sustainability and driving systemic change? So of course, this is work that cannot be done alone, and it's been my great joy for building communities of practices across disciplines, and also finding ways of how can embodied experimental and theoretical engagement coexist in our research communities. Also, to be able to work truly interdisciplinary, we need to build trust in each other, and through trust, there has been also been this great story of a lot of friendships evolving. And through this trust and friendship, I believe that we can slowly take these steps towards more collective action. With these words, I want to express my deepest gratitude for the people working in my group, past members, current members. They have been playing a really active role for getting all this wonderful work done. And then I also want to express my gratitude to Jaana Rich, Elisa Lassila, and Anne-Louise Bang for being great mentors. Better mentors that I could have ever imagined to have. So thank you for your attention and looking forward to discuss during the coffee break.